Hello, buddy. My name is Sanket, and this is our final demo on data streaming over RDMA.
This is Stacy. Stacy has a strenuous job, and she often comes home tired and hungry, only to realize that her fridge is completely empty. Now Stacy has to drive all the way to the grocery store, pick up all of her groceries, and then drive all the way back home. And then prepare all of the ingredients, cook all of the food, and only then can she finally sit down and eat. But this is far from ideal, as Stacy had to spend so much extra time and effort to do a simple task. What if there was a better solution? What if Stacy could have all of the prepared ingredients directly delivered to her? Now the only thing she has to do is pick up that food and cook it, and then she's free to eat. This is a much better solution, as Stacy can avoid all of that extra unnecessary overhead activity. Now let's apply this to a different situation. You're at home and trying to enjoy watching Netflix, but it's slow, unreliable, and causing you a lot of issues. Similar to Stacy's situation, the slowdown can be because of the extra overhead required by the data streaming protocol. What's the solution to this? Remote Direct Memory Access, or RDMA for short. Compared to other data streaming protocols, RDMA is faster and requires much less overhead activity. This is why we want to leverage the power of RDMA to provide a resource and speed optimized data streaming protocol.
Now I'm going to introduce the background on streaming. The market size of streaming is very large. The global video streaming market size was valued at $38 billion in 2018 and is growing at an annual growth rate of 18% from 2019 to 2026, and it will reach $149 billion in 2026. Another fact of streaming is that most of streaming contents are consumed on network TV and mobile devices. Video streaming contributes significantly to mobile data traffic, and it will have a higher portion in next few years. Therefore, improving performance and reducing costs of streaming tools are necessary for mobile devices. The global internet traffic on streaming is also increasing greatly. There is a high demand on server and bandwidth.
Streaming media is multimedia that is constantly received and presented to the end user. Streaming can be categorized into two parts: HTTP downloads and true streaming. HTTP downloads are modification of a normal download that utilizes traditional TCP UDP infrastructure. It has modified file formats, and it's slow and inflexible. By that, I mean server sends a massive burst of video buffers to the client, which plays the video from the buffer in hand. In case of true streaming, we have fully custom protocols. It's adaptive and also bandwidth efficient. Adaptive, I mean that the streaming server has a multitude of options, video quality options to choose from, and depending on the network conditions, it switches between them. While it's bandwidth efficient because the frame buffers are now significantly smaller as retransmission rates are much faster. We now introduce the secure reliable transport, our protocol of choice for the project. SRT was designed for low latency live video transmission. Some of its features include having fully controllable latency, supporting encryption, which means no unauthorized access to your video streams, and also having the ability to retransmit packet to maintain reliability. The video on the right shows a comparison between the live source and video being streamed using both standard UDP and SRT. And as you can see, the UDP stream in general has worse video quality and showing a lot of artifacts, while the SRT stream is, for all intents and purposes, just a slightly delayed version of the live source. Technically, SRT is completely video and audio codec agnostic, which means you can use any kind of compression to send data through SRT, And latency being of prime importance is in the order of 3 seconds or less and is completely tunable based on how much packet loss the user is willing to trade off. Use internal fields of SRT packet. SRT packet is traditionally enclosed within the UDP packet as a payload. The SRT packet consists of two major parts, the SRT header and the SRT data. The SRT header has auxiliary information like sequence number, encryption details, reliability details, the packet order, to name a few. It also has information about the timestamp and the destination socket ID, while the SRT data payload has the actual video data that is being transported by SRT protocol.
Now I'm going to compare TCP and RDMA. The RDMA stands for Remote Direct Memory Access. In TCP transmission, packets have to go through all these stages. TCP copies received packets to buffer, then copies them to the receiver. Therefore, they need operating system and CPU for data transmission. So, therefore, their CPU utilization is high. As we can see, the data in TCP goes a long way to get transmitted and has high latency. When live videos are transmitted, the high latency could be a trouble. Additionally, there may be a race between the HD video decoding and TCP since both of them have high CPU utilization. No matter who loses the race, the streaming can be frozen. The RDMA firstly establishes connection between the server and client. Unlike TCP, RDMA packets bypass OS involvement. The RDMA buffers are prepared to store RDMA packets. Then the data is written into receiver's virtual memory directly from senders, without system buffers. Since RDMA does not need to go through kernel, both its latency and CPU utilization goes low significantly. And reducing CPU utilization is very important to current streaming market. As we mentioned before, network TV and mobile devices are the main streaming devices. Both of them cannot have high CPU utilization for a long time, otherwise they may become overheating or run out of battery.
This slide compares between various types of RDMA technologies. Briefly speaking, we have three major types of RDMA technologies on the market today: IWAP, ROCE, and InfiniBand. We first look at IWAP, which is a mixed architecture. It uses RDMA verbs to work over existing TCP/IP infrastructure, and to achieve this, it modifies the upper layers of the TCP/IP protocol and uses a relatively complex NIC. InfiniBand, on the other hand, implements RDMA by using verbs, but also skipping over OS kernel involvement completely and utilizes fully proprietary low-level protocols and hardware. ROC is a more accessible solution that uses verbs, skips over OS involvement, but utilizes InfiniBand proprietary protocols at the low levels of transport and network, but switches over to Ethernet at the data link and physical layer, and also uses a relatively simpler NIC. Our project, though, focuses on ROCE version 2, which modifies ROCE to completely utilize TCP IP infrastructure and regular NICs. This makes ROCE v2 more accessible and therefore usable on NetFPGA.
We started with a purely software-based implementation of SRT on a Deter Lab test environment so that we could get a baseline measurement of the performance that we're trying to improve with our hardware-based implementation. So we had a server node that contained a server application and a client node that contained a client application. And we set up an SRT connection between the server and client nodes. Then we had a file that we wanted to transfer from the server to the client. and we conducted this experiment about 100 times, and we found that the average speed that the software-based SRT implementation was able to achieve was about 108 kilobits per second. So this is the speed that we're trying to improve with our hardware RDMA-based implementation. Let's go over the high-level functionality of our system. Here we have two nodes that are connected through a NetFPGA router, which includes our network processor. Suppose node 1 wants to send an RDMA read request to node 2. The application running on node 1 would need to call this function. The parameters in this function includes the local address, which is the memory address in node 1, the remote address, which is the memory address in node 2, and the length of the data that we want to read. When the application calls this function, we create an RDMA packet, which is then sent to the NetFPGA, where our custom network processor can recognize that it's an RDMA read request. And then we pull information from the memory location in node 1 or node 2 and then send it to node 1. Similarly, suppose node 2 wants to send an RDMA write request. The RDMA write function call looks similar to the RDMA read function call, but here, since the application is running on node 2, the local address corresponds to the memory in node 2, and the remote address corresponds to the memory location in node 1, and the length is the length of the data that we want to write. So again, this will be transformed into an RDMA packet, which is then sent to the NetFPGA, where our network processor recognizes it as an RDMA write request, and then it writes the data into the memory in node 1.
This slide talks about how the data flows through our process pipeline. As external data comes into the convertible FIFO and is completely stored, we start processing by first selecting the thread control 1 and fetching data from there. In the next clock, we switch to thread 2, and we have the thread 1 in the register stage. Next clock, we have thread 3, and each subsequent thread is now being pipelined through the processor. This thread cycling keeps happening until the processing has completely finished. This is done to avoid any data dependencies, which is a big advantage of using multi-threaded CPUs. Once the processing has been completed, the FIFO data is then sent out to the user data path to the next stage.
Here's a closer look at our hardware design. As you can see, we have the NetFPGA with our network processor and additional hardware components inside. When a packet first enters the network processor, it arrives in our combination FIFO SRAM. Our packet parser is then notified and begins examining the packet, which contains multiple 64-bit words. The packet parser will in particular look at the third word, which if the packet is an RDMA request would correspond to the RDMA header. This is the format of our RDMA header. As you can see, the first 31 bits is the RDMA indicator, which consists of a specific pattern that will help us identify this packet as an RDMA request. The next bit is the read-write bit, which tells us whether this RDMA request is a read or write request. The next bits of information are the local and remote memory addresses and the length of the data. The parser will first examine the upper 32 bits and see if the pattern matches with our set RDMA indicator pattern. If so, it will discard the packet and create a new 32-bit instruction. This instruction includes 5 RDMA indicator bits, a read-write bit, 5 bits for each address, and 16 bits for the data length. The instruction is then fed into our instruction memory and the rest of the pipeline. The processor then writes the information to registers that can be accessed by the RDMA driver, which actually conducts the physical read and write operations from the node 1 and 2 memories. We'll start off by programming the NetFPGA with our custom bit file. And now we'll enable the router kit so that packets can flow between the nodes. And now let's read the current memory contents in node 0 and node 1, which we'll be using in this experiment. Okay, so this is the current contents in the memory. It's the contents of node 0, node 1 interleaved. So you have the contents in address 0 here, address 1, and so on and so forth, and the data increments by 1 as so now let's try to start a server on node 1 and then send a write request from node 0 to node 1. So we're trying to write the data from memory location 1 in node 0 into memory location 2 in node 1. And we'll see if that's successful. So we can read the memory contents again. And now read the contents of that file. And as you can see, the contents in address 2 in node 1 has been changed. Now let's reset the contents again. Enable RKD. And let's do a read request this time. The read request will function similarly to the write request, but this time we're reading the contents in address 2 of node 1 and writing it into address 1 of node 0. So now let's read the data in the memory. As you can see here in node 1 and address 1, the data has been updated to align with what's in node 1 address 2.
Thank you.